easily as it is now, so I wouldn't send somebody out to get something. But I think we're in good shape.
We're
busy.
Yeah, totally.
Okay.
No, leave it, because
So,
Mike, you know how to do that.
today, despite the environment, I think we're going to do pretty well. And what we're starting with is AC circuit theory, and you may notice that this morning I woke up and said, oh no,
It's on picture,
because I looked at the chapter titles to make sure I had a good set of review material, and I forgot that we ended in mid-chapter for midterm 2 when we left AC circuit theory off. And so AC circuit theory had to appear here. And before I solve the first problem, I want to just remind you guys of a few relations that are going to be critical in doing AC circuit theory, because we're doing AC circuit theory using complex numbers. And complex numbers mean that the number is partly real and partly imaginary. And the interesting thing about complex numbers is that the algebra that you perform is pretty rudimentary. It's much easier than sine and cosine, and all the I does is it makes manipulations of things like phase very easy. So, a complex number, for whatever reason, it is traditional to call almost all complex numbers, even in your math class, Z. It may be because in your math class, since chalk only does 2 dimensions, and the mathematician used X and Y when they got to the complex number, they called it Z, just because of alphabetical order. I don't know why, but a complex number could be written as A plus I times B, where A and B are real numbers, so that it's explicit what part of this is imaginary. It's the real number B multiplied by the I. Now, when you think about this thing in the complex plane, you can think of it as a location whose x-coordinate is A and whose y-coordinate is B. Yes? Sorry? I didn't hear the question.
When you watch the video, the writing it's like in your image. Do you know how to fix that?
That? Better? Okay.
Then we can't use it.
Now, there's a second format of a complex number that is, thanks to our friend Mr. Euler, and in fact, if it weren't for this relationship, there wouldn't be any advantage to using complex numbers. And the relationship is that this same number Z can also be represented as a magnitude and a phase. Now, if you ever want to add 2 complex numbers or subtract 2 complex numbers, you want both numbers in A plus IB. So that's why when we begin a problem and we start to determine what's the impedance of a circuit, we take the format of the numbers in A plus IB and we add the resistor, which only has an A, to the inductor that only has a B kind of term, and we add them up in this format. However, if we want to multiply or divide, then it's much easier to write the numbers as C e to the I phi. Because in that place, to get the result of the multiplication, whatever are the 2 coefficients that are magnitudes, you multiply those, you get the magnitude of the result, and then when you multiply the 2 e to a power times each other, it's e times the sum of the powers, and therefore you've got the phase. Very simple algebraic manipulation. Okay? So in the course of solving a circuit problem, we're going to have to add to get the total impedance. We're going to add the impedance of the resistor to the impedance of the capacitor. And so we're going to want to start in A plus IB. However, every other manipulation throughout the course of the problem is going to be multiplication and division. So for that reason, we're going to want to put all quantities that we know of into the form C e to the I phi. Okay? So, the first thing to be able to do is to be able to take complex numbers and go back and forth between the 2 versions. And if you have A and B, and you wish to find C and phi, How is C related to A and B? Square root A squared plus B squared. And how is phi related to A and B? Inverse tangent of B over A or A over B? B over A. B over A. If, on the other hand, and we actually don't do this often in analyzing circuits, but someday it might come up. If, on the other hand, you had a complex number that was expressed in terms of C and phi, how would you get A and B? What's A?
D both sides.
And how would you get B?
D side.
Yep. Because the triangle that you imagine for every complex number looks like a triangle, has an x leg of the triangle of length A and a y leg of length B. It has a hypotenuse of C and an angle with respect to the x-axis of phi. And so these relationships should take you all the way back to vector manipulation. And even though I haven't drawn a picture, they should be clear in everybody's mind how they work. Is that good? Yeah.
Just go over what phi is.
Phi is a phase angle. When we were working with vectors, we would have two formats for vectors. Components, as well as magnitude and direction. In that case, the direction was given by an angle. Well, it turns out that direction is not so meaningful in an AC circuit. What's the direction of your AC circuit? But every quantity in an AC circuit goes up and down. The voltage that you apply, dun, 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 dun. The voltage that appears across the resistor, dun, 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 dun. The current, up and down, up and down, up and down, up and down. Actually, for the current, you might even want to say back and forth. And the voltage on the capacitor, up and down, up and down, up and down, up and down. Every quantity oscillates. However, the interesting characteristic of the AC circuit is that these oscillations are not always matched in time. The moment at which the current is highest, and the moment at which the power supply is highest, and the moment at which the voltage on the resistor is highest, and the moment at which the voltage on the capacitor is highest, these are not all the same moment. A couple of those in that list are the same, but most of them are different from one another. So if you were to look at it on an oscilloscope and see waveforms, you'd see waveforms of some height, and they'd be shifted with respect to one another. And we know that when you go from sine to cosine, that's a shift of how much? Pi over 2 radians or 90 degrees. Because the only difference between a sine and cosine is sliding it along the axis. So these waveforms, what does the current as a function of time look like? You can't express it as sine or cosine, but you can say that it slid as compared to the reference, which is the power supply, by such an angle. And this represents the angle by which something is off. And as it turns out, the way that we do this analysis is every quantity has a magnitude and a phase. Since phases are really just compared one to another, we take as a convention that the voltage of the power supply is the thing whose phase is the reference for everyone else, what we would call a phase of 0, and then all other phases are compared to that. So the impedance of the circuit has a phase, the current through the circuit has a phase, the voltage across the resistor has a phase, and the voltage on the capacitor has a phase. And then in order to solve the problem, every quantity needs to be expressed as two numbers, magnitude and phase. And so what we'll be doing is we'll be adding and subtracting like this, and then magnitude and phase will come out like that. And multiplying is a bit easier, because multiplying, you get the product of the magnitude and sum of the phases. And then that gives us every quantity we want. Now, expressing a quantity as a magnitude and phase means that you're then equipped to draw an oscilloscope trace that goes up and down in accordance with the magnitude and is located in accordance with the phase. And there are some problems here in which we take the phase seriously and we draw the curve at a particular location in accordance with it, okay? So it starts out with just calculate them, and then at some point the problems move on to the, and do you understand what those numbers are? So we'll work our way through that with the problems, all right? Now, just for convenience sake, I wanted to express a few things in two different notations. I want to express the impedance of a resistor in A plus IB. I want to express it in C e to the I5. And I want to do the same thing for an inductor and the same thing for a capacitor. Okay? What's an inductor in A plus IB form? What's a resistor in A plus IB format? R. What's a resistor in C e to the I5 format? R times e to the I 0. And then e to the 0 is 1. Because even when you multiply I by 0, you get nothing left. Okay? So that's the boring one. Suppose I express an inductor in A plus IB format. What do I get for its impedance?
I omega L.
Okay? That's an amount of omega L purely in the plus I direction. Okay? What do I do if I express this in C e to the I5 format? What's the amount?
Omega L.
Omega L. And what's the direction if you're in the positive I coordinate? Not 0.
Pi over 2.
Pi over 2, or 90 degrees. But since we're getting into fancier mathematics, we'll stick in the radians. Both of those are ways to express the Z of the inductor. Which one of those will be most useful in additive? The left column. What's going to be most useful in multiplicative?
Right.
The right column. When we're busy finding the total impedance of a circuit, we're going to use the left column. When we're busy later calculating what's the voltage across the inductor, we're going to use the right column. Okay? And how about a capacitor?
Negative I over omega C.
So, what's the magnitude of this?
Negative 1 over omega C.
Disagree. Magnitudes are never negative. 1 over omega C is the magnitude, and the minus sign is coming from the direction, because your phase is negative 90 degrees. Minus I pi over 2. Okay? Yes?
Those e to the I pi over 2s, are they a calculation or just a thought process of thinking about the voltage?
I can do it with a calculation because I can be written as 0 plus I times 1. Okay? Then in that case, I can get the phase by saying that I need to take the inverse tangent of 1 over 0. You may say, wait a minute, inverse tangent of infinity? What's the curve for tangent look like? It goes up to infinity. Where does it go to infinity? Pi over 2. So in fact, by taking the inverse tangent either of positive infinity or of negative infinity, that will take care of the I on your behalf. So the inverse tangent of positive infinity is plus 90 degrees. The inverse tangent of negative infinity is minus 90 degrees. And that's where these two are coming from, if you like. Okay, so the thought process gives you the same answer because it's all the same calculation. Yeah? Yeah, in principle. It will be a pain in the butt to interpret later.